Good afternoon, and welcome to the second plenary lecture of the third day of the EMI 2013 conference. Thank you for being here today. So I will be serving today as chair of the conference and chair of this session. When you organize a conference, you have a lot of headaches, but a few advantages. And one is to pick the session you want to chair. And of course, I was and the plenary speakers to some extent. And it's my privilege to introduce to you Dr. Roland Pellenq. He's a senior scientist and head of the CNRS MIT Joint Laboratory on Multiscale Material Science of Energy and the Environment. And he's also co-founder and lead scientist of the Concrete Sustainability Hub at MIT. And he graduated in 1994 with a PhD in chemical physics from Imperial College. And today we'll be talking about cement and multi-scale porous material under the nanoscope. Roland?
Thank you. Do you hear me? You have some sound? Yes? Okay, well, thank you, Giancarlo, for the introduction. And well, it's my great honor to be here today. And before I go on with the talk, I would like very much to introduce my co-authors, because there are several connections with this place. First, well, Franz Ulm, for sure. I just remember that he was a postdoc here for some time with Zdenek Bajant. But then you recognize Harlin Jennings. He was here for a couple of years, right? Like a couple of 20 years, maybe. Then you have another guy called Bajant. I don't know if you heard this name before. It's Martin Bajant. And that tells you that we can manage to convince Martin to do cement. So now cement has become a real family business in the Bajant family. So, okay, then who else? You have Christian Hoover. He did his PhD here. Where's Christian? He might be sleeping somewhere. Oh, here. Not yet sleeping. Sorry. But then I have to acknowledge MJ, Mohamed Javad, coming here. He's one of the main guy behind all the nanoscale thing I'm going to talk about, together with Dr. Bushi here. And these guys, Enrico Massarero, Elena Sokolova, Matthew Pinson, Patrick Bono, are the guys running the mesoscale, because I will try to bridge scales. And so you need to know who's behind those things. And then we have a couple of guys doing experiments, so Christian Hoover, Konrad Krakowiak, together with some other colleagues like Marcus Buller, the new head of civil engineering at MIT now, Christine Van Vliet, Sidney Yip, Martin Bajant, Franz Ulm, and Harlin Jennings. And without forgetting about those guys, these are close collaborators. Jeff Thomas, he was here before, I understand. Emmanuel Delgado from Zurich, and a bunch of guys from Marseille, my former lab, which I convinced to get some interest into cement. So now my next thing is to introduce, to explain the title. Cement, you know everything. Multiscale is all over the place. Okay? Now, what I need to understand, to explain is this nanoscope thing. So don't expect me to introduce a new imaging technique, like a new super microscope. The nanoscope is rather a suite of concepts combining experiment as much as simulation. And simulation is here like the cement, if you like, between different kind of highlights from experiment. So that's the idea of beyond the nanoscope. And when I say simulation, you'll see that this special kind of simulation is really based on a kind of mechanics that I rather do, which is called statistical mechanics, more than continuum mechanics. And it all has to do with grains in interaction, whatever grains they are. It could be atoms, molecules, could be electrons. When we started with Roosbay, I saw Roosbay here. He was the guy doing the first quantum calculation on tobamorite for some years ago. And then, so you have interactions, but then you can also upscale the ideas and having interaction between blobs or big grains, okay? And the idea is to have a frame of ideas, a frame of concept that could be used all the way. So we're going to apply this to cement and see how far we can go in comparison with experiment. As much of experiment we can get. Could be scattering, one angle, could be nanoindentation, could be, well, we're going to talk about creep at some stage and so on. All right, so this is what we do. This is the kind of roadmap of the CSH Hub, is to do a combination of multi-scale modeling as much as multi-scale experimentation, combining different simulation techniques here and different experiments And this is what this nanoscope is really a combination of simulation and experiment with a very ambitious goal, because we want to bridge scales, in length scales, so starting from atoms up to micron, because we have this feeling, obviously, that finite element method then will take over and do their job. So we're kind of providing the elementary voxel of those discrete methods. And not only we want to bridge length scales, but we want to bridge time scales. So the scale of PS is picosecond, 10 to the minus 12 seconds. This is the characteristic time scale for chemistry, for reactions, right? Up to years because of degradation, because of creep and so on. So it's very ambitious, and you'll see how far we can go up to now. And then you have here the length here, and then this is real things, real experimental, image, and these are different models that you're going to see all the way through this presentation. Right, so I'll tell you about some experiments. That's my only experimental slides. That's just to tell you that these are kind of experiments we designed in the CSH lab at MIT. First would be by measuring the chemistry. And when we deal with cement, it's a complex material also because of its chemistry. It's not a well-defined compound, it's a non-stoichiometric compound. So by throwing X-rays to a cement sample here, we can detect the elementary composition at the scale, say, micron, or a little bit below micron. For instance, here you have a 3D plot of aluminum content, silicon, calcium, and you can actually look at CSH, the glue. I'm going to focus actually on CSH most of the time, all the time, here in a real cement paste. What we do, this is really Franz Ulm and his team doing experiments, is also doing nano-indentation, so you nano-indent, but not only once, just this little triangle, but you do an array of nano-indenting of imprints, and you run a statistical approach pretty much the same way as you do with the WDS measuring the chemistry, and then you can now access to hardness or stiffness here of different phases, and this is how actually Franz Ulm and Jennings in a couple of years ago, 5 or 6 years ago, were able to say, okay, CSH is made of two phases, low density, high density. Okay. And that's really new. This is a very new technique that is taken from the biofield, actually. This is a micron droplet of water in which you can put one single piece of C3S, of clinker. And the whole thing is in oil, so not in contact with air. And the idea is that with the camera, with a fast shooting camera, you can actually look at the hydration kinetics of one single grain of C3S, for instance. And obviously, we run other things like NMR to measure the quality or the texture of CSH, for instance, in addition to other adsorption and so on, more classical techniques. Right. What about the simulation? And this is the main focus of this talk. Clearly, the idea is to start at the right place and formulate realistic models of what we call dirty material, dirty porous material. That could be kerogen in shale gas application as much as cement or other things, right? And the idea is that we run atomistic simulation in the first place and mesoscale simulation. Different flowers means different way to do statistical physics, but still everything is in the frame of statistical physics. And obviously, we do it in the bottom-up approach. We start from the nanoscale, and we hope to connect to larger scales. And then, obviously, we want to compare with experiments and for instance, do adsorption of water in cement, for instance. We could do freezing. You can measure different mechanical properties, strength, and now fracture. And you can also look at transport properties. Could be a flux of molecules through those porous matrices. Could be as much as heat conductivity. Right, so the idea is to understand, by all those measurements, even if they are numerical, they are still measurements in some ways, right? And compare with experiments. And the idea is that once you understand them, you may improve the material itself at different scales. Excuse me. All right, so I have some couple of slides, and we're going to start the afternoon by doing a bit of statistical physics, easy one. So first, nothing very new here. It's just a very general features of what we can do. Why is these days atomistic simulation based on statistical physics so useful in industry, for instance? Just because you can do measurements of things that are very hard to measure in real life. For instance, look here, long chain hydrocarbon properties. For instance, This is the simulation, atomistic simulation technique that allows you to measure the surface tension of very long alkane chains. The experiment is very hard to do. And those measurements of surface tension of those, for instance, alkanes here, are the input of chemical engineering modeling that run the plant. Okay? And you can go along with many aspects and tell you that these days the pharmaceutical industry will run simulation in the first place before even doing the real synthesis of molecules. Okay? The same for microelectronics. They will run atomic simulation before actually to guide the development of new electronic devices. Obviously, you can use simulation as a way to validate ideas or prove wrong or true some ideas. For instance, is the Kelvin equations, that is a macroscopic equation, valid in nanopores that we have in cement, for instance? The same for diffusion, for instance. So I'd like you to consider the simulation as a real third route in between real experiment and theory. This is just, we can say that as a numerical experiment, a clean numerical experiment. There is no leakage, temperature is well defined, and so on. Okay, and I like this slide because it's kind of, the numbers you're going to see are kind of 7 or 10 years ago old, but this is the kind of argument that the industry likes very much to see. If you were to measure all the vapor-liquid equilibrium for every compound, mixtures of compounds, right? It will cost you a one state point for at one temperature for some binary mixtures will cost you $3,000. It takes you 2 days. If you were to do for all non-compounds, you go down to this crazy number, $180 trillion. It starts to be some money, right? So simulation is not just some kind of excuse for academics to spend the time. It could actually be something very important even for the industry. All right, so here is my little part of my talk on doing statistical physics. I don't want you to read this, just concentrate on this table here. If you want to do statistical physics, you need to work with some constraint, and not any constraint. It's got to be at least one extensive variable, and you can choose the rest. For instance, if you want to imagine that you consider volume, it means that then you can calculate pressure as an average, as an ensemble average. If you have number of molecules fixed, then you can calculate the chemical potential as an average. Or if you fix the chemical potential, you can calculate number of molecules. Okay? It goes in both ways. But still, we need to have at least one extensive variable. So, here is my game. Can you tell me, Christian? Random, right? What kind of real statistical ensemble can I build here? For instance, at least one of these, but it could be 3, so I can do an NVE ensemble, right? So with those, I know how to average things, okay? So this is called a micro-canonical ensemble. Not very useful because you need to work at constant energy, and this is not very useful. But still, in this ensemble, you can define actually the entropy very easily as a number of complexion, number of realization in the system. Other more useful ensemble, for instance, Christian, you still here? Okay. Pick one extensive variable, n, okay? And I can go npt, okay? That will be a decent statistical ensemble. What can I do with this? You see, I have npnt. When pnt, I can design or derive a phase diagram of a compound or something. Okay, that's the way you do it theoretically, right? It could be water, it could be whatever you want. Another ensemble that I like very much is the mu-vt. It's called the grand canonical ensemble. It's very good because if you're interested, for instance, in water, in the adsorption of water in cement paste, right? You control the water with the relative humidity, P over P0. And P over P0 has an easy connection with the vapor of the water chemical potential. Okay? So basically here is related to the vapor pressure, and I can derive the number of molecules that get into the system at constant temperature. So this is a mu-vt ensemble. So what is the experiment you get to compare with? It's the relative humidity here, the number of molecules in the system at constant temperature. This is called the adsorption isotherm. Okay? So if I want to do water adsorption in cement and compare to experiments, I will run a grand canonical Monte Carlo simulation, a mu-VT simulation. Okay? And you can design, with the restriction to have at least one extensive variable to fix system size, you can design as many ensembles you want. So the idea is what you want to measure, what you want to compare with experiment. Again, if you fix the pressure, then you can calculate the volume and compare with some, I don't know, structure experiment, for instance. All right. So there are two ways to do the job, and they are equivalent. They should be equivalent at equilibrium. The first is known as Monte Carlo. Monte Carlo, maybe you don't know, maybe it's a small city. It's an independent state in the south of France for very rich people. And it's called Monte Carlo because they have a very nice casino there, and they pick up random numbers to run the casino, right? So this is where the name comes from. So Monte Carlo simulation is one way to do the job. The other one, maybe you're more familiar with this one, is called molecular dynamics. But again, they are strictly equivalent. In both cases, we always need to pick an ensemble, a statistical ensemble, so that we know what we do, we know how to measure things. And then we have interacting particles, so it means that we need to specify the way they interact together, the potential between them. So that's the second ingredient. The first is the ensemble, then the technique, MD or MC, and then is the way the particles interact between themselves. Obviously, if you are dealing with a pure fluid, you need, or let's say a polymer, you need to specify interaction between chains and also the intra-interaction between, because these are flexible molecules. But then if you are to absorb this polymer at the surface of a clinker grain of cement, for instance, you need to specify the type of interaction you have with the solid phase and the polymer, for instance. Okay? And then once you're done with this, then you run the statistical mechanics. You solve the equations exactly, numerically, so there is still some error there, but there is no other further approximations. To tell you that in the end, the only approximation we have is the choice of this, of the three, if you do the statistical work properly. Okay, so let's go to some equations. When we do Monte Carlo simulation, we are dealing with stochastic matrix. Basically, we create configuration following a chain, a Markov chain. And here is the master equation that propagates in time the probability of having the configuration I at time t plus 1, an increment of time, starting from time t. And what you have here is the probability of all other configuration j to become I, multiplied by the probability of existence of those other configuration j's, minus the way to leave I configuration towards j's, and this is what's written here. At equilibrium, you understand that the whole thing will be equal to 0, okay? And we left with this kind of equation here, where the sum of all the states j's going to I times the probability of j's to exist equal to p of I sum of the probability of leaving the state. And there is one condition that satisfies this equation, is this one here, and it's known as detailed balance equation. Well, this is just Monte Carlo simulation. So basically, now we can actually do something like do the ratio of those two W's and the P's on the other side here. This is what we have here. And you see that here, these are the probability of J to exist. And in physics, it's linked to energy through the Boltzmann factor. That's the good thing of statistical physics. We don't have to prove the existence of the equation because nature is very nice to us. And we know that a configuration will exist with a weight, which is this exponential minus E, the energy of the configuration, divided by KT. By the way, here, this is the energy. And we have a very strong feeling about energy in physics. There is no temperature in business here. This energy comes only from interactions. This energy depends on the relative configuration of molecules and electronic properties of atoms. There is no temperature in business. There is no like dissipative things in it, right? It's just pure potential energy. I'll come back to this point here. So then you can reduce this term here, and you have exponential minus delta T over KT, which is the energy difference. Now there is a little thing here that tells you about Z. That's not in the expression. I need to define what is Z in the first place. Z is the so-called partition function, which is the sum of all accessible states, the sum of I exponential of minus E over KT of all states. That you don't know. And if you open any book of statistical physics, you'll see that the Z is a very central function, because once you know it, then you can derive any function, including entropy. The problem is that you just don't know all the states. Okay? And this is where the simulation is very smart, is that actually you don't need, actually there is no z in the expression here, where you just propagate, create a series of configuration in Monte Carlo simulation according to this recipe here, and basically you're going to find the one that are actually contributing, the stable ones, the one with basically the lower energy, without knowing z. So in many ways, Monte Carlo is a smart MD, you'll see MD, or MD is a stupid Monte Carlo, the way you want. Okay, so this is just the algorithm. The whole thing, I mean, to make it working, these guys, Metropolis Teller, Mr. and Mrs. Teller, Rotenblatt, Mr. and Mrs. Teller, they had a dinner some time ago, in 1953, and at the end of the dinner, they say, okay, what can we do? Play card? No, they didn't play card. They derived the algorithm, apparently, and that was just published in this J. Kempf's paper here. So basically, when the energy going from one state to the next, when the energy goes up, you have to evaluate the weight, I mean the probability of having this. Otherwise, if the energy goes down, the probability is yes, it's going to happen. Very easy algorithm. Okay, so we have a valid Monte Carlo procedure if we generate this Markov chain in a good way, and if it's called ergodic, which means that you're not trapped into some kind of situation where you cannot escape, you're not sampling the whole configuration space. And this could be, for instance, you cannot work at t equals 0 with Monte Carlo. You get stuck in local minima and not finding the true equilibrium, for instance. Right. Now, what can we do with this? Because the whole idea is to average, right? So to take some average of some given properties, whatever they are, okay? And this is the definition of average. You see, this is the property, the value of this property for a given configuration, where P are momentum or positions, multiplied by the probability, by the Boltzmann factor, the probability of existence, which is the Boltzmann factor divided by Z. That is the thing, the partition function. And here you see that this exponential is h. It's written in a very physicist way. We call it Hamiltonian. Wow, okay. Hamiltonian in classical mechanics is the sum of it's always the sum of kinetic energy and potential energy. But you see, here I've written things with momentum and V's and position, assuming that I can actually split variables. And that tells you that this way to write things is actually the classical mechanics way to write things. Because if I was to do quantum physics, I just cannot separate those. Okay? So now the question is, you all learn about quantum physics, right? This is the physics for small particles. Atoms are small particles. They should be quantum particles. And then we have now a very neat way to decide if we can treat, for instance, water molecule in cement as a classical particle or a quantum particle. Actually, this is called the de Broglie wavelength. It is h, the Planck constant, divided by square root of 2 pi mkt. M, the mass, T, temperature. You see, it depends on the mass and the temperature. Basically, what this is a length. So basically, when this de Broglie wavelength is comparable to the system size, to the size of the molecule, for instance, then, for a given temperature, of course, then you have no choice. You have to do the whole thing quantum. And then you cannot separate those variables anymore. And you don't run with the Boltzmann statistics. You run with the Bose-Einstein for spin equal to integer value of spins, or to the Fermi-Dirac statistics for half integer values of spins. Okay, I can tell you that water in cement can be seen as a strict classical particle. Good news. Okay, and then we do the averaging by chaining configurations. Right, what about MD? But MD is very close to mechanics, to your mechanics, because basically we're solving Newton equations of motion, okay? For classical particles, so we need to make sure that we are dealing with classical particles, because Newton equations are for classical bodies, okay? And then what's interesting is that in Monte Carlo we were doing average of a configuration that were created through this Markov process. With MD we solve things through times, okay? So we solve the equation of motion, Newton equation of motions. And so you have this, you can take an average over time. And what is very nice in statistical physics, providing that you do the job correctly, either a Monte Carlo by statistical average of an ensemble, or for time long enough, you should get the time average equal to the ensemble average. This is why I was telling you at the beginning that both MD and MC should be doing at equilibrium the same job. Okay? The first MD was run in 1957, and I have here a little story, which is like 10 years, well, a few years after this first paper, a Frenchman called Lou Verlet derived an easy way to solve numerically the Newton equations. Okay, it's known as the Verlet algorithm. And then in 1980, Verlet stopped doing theoretical physics research. He went into how Newton came up with those ideas. So it was more like on history of science. And Verlet discovered that Newton, 200 years before him, was actually using the Verlet algorithm. So 200 before him. So Verlet now calls it the Newton algorithm, actually. So it's not the Verlet algorithm. To discretize trajectories of bodies in space. Okay? Right, so this is a summary of things. So we play with particles in the box, with interactions in Monte Carlo, specify an ensemble, in both cases, MD here, generate move with this Markov chain, average, take the probability of those to exist, average, and obtain equilibrium property. Do the same with MD, plus one thing, that MD also works with non-equilibrium. Okay? So this is why, maybe MD might be seen as superior than Monte Carlo. Monte Carlo, to have a meaning, has to be at equilibrium. The thing is, I was telling you that Monte Carlo is a smart MD, and MD a stupid Monte Carlo. Because in MD, you're going through all states, through times, including non-stable states. While in Monte Carlo, in fact, you're just going to stable states or metastable states. Okay? So if you were to work at equilibrium, probably, if you are looking for equilibrium property, maybe you want to consider Monte Carlo in the first place. For sure, MD can run non-equilibrium situations. Right, so this is again a summary in the sense that we want this is the condition of running simulation these days. Typically, we run tens of thousands of atoms these days, maybe up to 100,000. A few examples in literature where people have been playing around with very large numbers to very large times, but this is at the expense of the quality of the potential. They were using super simple expression of the interaction, probably art spheres. Okay? Okay. And then I need to go back to cement at some stage. The art of simulation is the choice of the correct description of interactions. If you don't have the correct interaction, you cannot expect to be able to compare with the experiment. So for instance, in the cement glue, the cement hydrate, CSH, at the nanoscale, you'll see that we use the so-called ReactFF force field, which is a force field that is classical, but still is able to mimic the chemical reaction, for instance, the dissociation of water and the condensation of silica chains, for instance. So you have a way to take into account the chemistry, the bond breaking, the bond forming. At the mesoscale, you'll see that we use an effective Lennard-Jones form, which is a very simple form, to describe the interaction between grains. Each grain, you'll see, is probably around 2,000 atoms. Okay? So the whole game of the simulation guy is to choose to design the way particles are in interactions. Let's go back to cement. So that's a picture taken from Hamlin Jennings's work, 2007, where this is a SEM picture at the scale of microns of a CSH paste. You see this is kind of a messy material. Multiscale for sure, you have very big pores at the scale of micron or tens of micron that they call capillary pore in the cement business. You have a CH, which is Portlandite here. You have the glue, which is the gray phase all over the place here, which is called CSH. This is also porous matrix. And you still have some remaining unhydrated clinker grains. You know, cement, you put the cement sack into water. So these grains are called clinker. And these are the clinker that have not fully reacted yet in this cement paste. At the nanoscale, what do we know? At nanoscale, this is probably the most resolved picture of CSH. There is no distance here, but you have to know that the distance between two layers here is 1 nanometer. So you almost see the atoms. Okay, so this is a zoom out of this picture here. And if you read cement literature, so very often, or always, I should say, cement or CSH is referred as being close to a crystal called tobamorite. Okay, and but clearly this is not a crystal because it doesn't diffract. It doesn't do diffraction in the same way as tobamorite. I mean, the real cement is. You'll see that it's more like a messy material, even at the nanoscale. Right. What do we know else? What else do we know? We know the work of Alvin Jennings and Franz Sulm in this CCR paper a couple of years ago, 5 or 6 years ago, where they were, by doing nanoindentation and by solving, solving the M and H experiment that is the output of the nanoindentation, they were able to find out the packing fraction. And this is how they came up with this very interesting thing, which is a paste of CSH will have at least 2 densities, one at 64%, one at 74%, and maybe one at 86 here. And obviously, they said, oh, very easy, 64% is the packing fraction of random spheres. Okay, this is what you have here, a bunch of oranges in a box. 74% has to be something like ordered. That's the way to pack in a cubic lattice the same oranges. Obviously, they're wrong, okay? Because nobody has ever seen a cement as ordered as this at the mesoscale, okay? We'll see why before, in a minute. But so this is because they were assuming same size particle. And they were right. I mean, if you are running a box of same size spheres, the random packing of those spheres will be 64%. And the order packing of those same size sphere will be 74%. So that will be the easier kind of idea coming out of those experiments. All right, and what about the size? Then Alvin Jennings, in this very famous paper with Allen and Thomas, Nature Materials 2007, they did small angle scattering here, and by analyzing this curve, you see about the shoulder here, you did 2 pi over Q vector is the momentum transfer vector. You come up with a size of 5 nanometers. So those oranges have a size of 5 nanometers, okay? But there is a problem here, because if there were to be same size particle, we should be having a very oscillating scattering function. And clearly this is not the case. So we knew for some time that something was wrong with this idea of having ordered or disordered packing of oranges with same size oranges. And the answer you can, guess the answer. The answer is that you need just to have more of size in the business. So by including the polydispersity, you will see that we can actually go back to many properties of cement paste. Right, what about the nanoscale? Nanoscale, we still have a problem because I was telling you that cement has something to do with tobamorite. But tobamorite, in terms of composition, measured at the calcium over silicon ratio, is right here, between 0.6 and 1. And cement has a composition between 0.2 and 2.2. Something is wrong with the chemistry. It cannot be tobamorite. Often you read Richardson and he will say, okay, no, cement is actually a mix between tobamorite and jenite. That is true that jenite has a C/S ratio of 1.5, but if you do an average, usually the value is in between, not outside. Not so good in mathematics, but okay. Okay, so here is our strategy to sample the whole thing, the whole chemistry of cement. We know we have an exact limit, which is tobamorite, C/S equal 1. So we start from there. And what we do is we randomly remove some silica SiO2 tetrahedron in the structure. With this, we maintain the electroneutrality of cement because SiO2 is neutral. So we just create defects in the structure starting from the crystal. Okay, then we dig into it. So by removing Si, we do increase C/S. Okay, so then we can span the values. But we realize that as soon as we do an NPT, so remember the statistical physics and so on. So we do an MD, molecular dynamics, at constant number of particles, of atoms in the box, constant pressure on the system, in this case 0, constant temperature, 300 K. What happens is that you start having, by creating disorder in the layers, and even creating cavities. Now, if you run water adsorption again, now I will use this grand canonical Monte Carlo, which is the good technique to do the adsorption. I will see the water going all over the place, including in those cavities. Okay? And then I can start measuring, or in simulation at least, properties like elastic, shear, fracture, and so on. And I have to tell you something, that the recipe to define the interaction between atoms and the substrate, and the atom in the substrate, are all done within the frame of this REACT-FF, this reactive force field, which is a new force field from Adrie van Duin from Penn State University, and it's really mimicking the chemistry for those light elements like silicon, calcium, oxygen, and so on. Okay, so this is why we designed the secret project, not with the S, but with a C, because we go combinatorial. Because you understand that there are many ways for a given constraint, a given CRS value, there are many ways to cut samples. Okay? So it's got to be combinatorial. We need to explore all of them. And this is why we ended up with 150 plus molecular model of CSH, spanning the entire range of CRS between 1 and 2. Okay? And then we need to compare with experiments, of course. So here, the first plot is the amount of water in the system. This is the total water that was put in the system with the grand canonical Monte Carlo simulation, and you can see that it compares very well with drying experiment for those triangle here, and from neutron scattering experiments for those blue triangle here. So we're right on the right place. The curve here tells you that this is what remains real water molecule at the end of the simulation process, because about half of them have split and have become OH group attached to the structure. Obviously, when they do drying experiments, they will heat the sample up, and those OH groups will recombine into water. They will be measuring water molecules, right? But about half of the water that goes in the system becomes OH groups attached to the structure. So and there is a way from inelastic scattering experiment to measure the number of those, for instance, CaOH groups here. And these are the triangle here, here, and here. And you see that, again, the simulation gives a good result. Another way to probe the structure is to run solid-state NMR. It tells you about the state of the silica, the silica regions in the CSH models. And for instance, it tells you you can measure an average length of those silica chains. Remember that in tobamorite there are infinite chains. Now with the defective model of CSH, they are much shorter. So tobamorite is 1, so we have the chain that runs to infinity up here. And these are experiments. The triangle again an experiment. So the blue line is just a guideline to the eyes, and in between we have the simulation. So we are right again. There is one more thing to say here. You see that at one given CRS here, it looks like you can get different values for the same paste. That brings a new concept, which is I think new in the cement business, is that CRS is not enough to define everything. And actually what we have is what the mineralogist guys call polymorphs. Same chemistry, but probably different molecular arrangements. And they exist for one given CRS. These two things here are, one is a way to probe the short range. It's called EXAFS. So this is a pair correlation function. This is me being a calcium atoms, the probability of finding any neighbor. So the first peak is oxygen, the second is silicon or the calcium, and so on. And this comparison with the experiment, you see that in experiment, in blue, the width of the peaks actually are even wider than the simulation. It tells you that there is quite some disorder at short range. Doing diffraction is a way to probe long-range order, okay? And he'll compare here the experiment, again in blue, with one of the model at CRS called 1.7 here. And you see that we have something which is, well, at least quite close, but at least we do not see those tobamorite peaks in gray for the crystal tobamorite, which obviously being crystalline, meaning that he has lots of ordering. A crystal is a very ordered structure, and CSH is not. Okay, now we can analyze the structure. We just comment this graph here. This is the modulus in plane, because still we have layers, and in between plane. M1 is in the plane, M3 is in between the layers. And you see that with increasing C over SC, what we have a transversely isotropic CSH structure that becomes isotropic CSH here. We can reformulate the same thing by measuring the isotropic Euclidean norm, and we have actually a transition at around 1.5 from a 2D structure to a 3D structure when it comes to measuring mechanical properties. Okay. So I'll come back now to this concept of polymorphism. For one given chemistry, I was telling you that there are different ways to do different models. Okay? And what is interesting here is that you pick one, say this one, 0.5 here, 1.5 here. You see that all those things have the same free energy, almost the same free energy. But they can have very distinct elastic response. So that tells you about that concept of polymorphism is probably key in understanding the nanotexture of CSH at the nanoscale, of course. And if you do the more complete analysis, you'll find that the fact that you can get for the same free energy different elastic response is due to the actual arrangement of the silica chains, or the chunk of silica chains you have. So the NMR, solid state NMR, is probably the good way to select a good CSH, for instance, the one that has mechanical properties around 90, or elastic properties around 90, for instance. That could be seen through NMR, should be seen through NMR. Right, now that's the work of Mathieu Bauchy, because this guy is a glass physicist, and he joined the hub by importing this rigidity theory, which is around for some time, and actually, if I remember well, is due to James Clerk Maxwell, analyzing macroscopic structures like this iron thing in Paris, that stands in Paris for some time. But so the idea is the following, is that the number of constraints in a system, when it's smaller than the number of degrees of freedom, you have a floppy structure. If the number of constraints is larger than the number of degree of freedom, you have another rigid or stressed rigid structure just like that thing here. And then there is a special case, which is the isostatic case, where the number of constraints exactly equal to the number of degrees of freedom. So what did Mathieu is he adapted this to the small scale and applied this to CSH. So we need to define a number of constraints per atom and apply the same rule and see how we can kind of discriminate different CSH with this new way to see CSH. And this is, at some stage, you need to define what is a bond. So what you do molecular dynamics. So you have a trajectory, and you follow in time the system, and you say, okay, when the atoms are not going away very much in time for a given temperature, you say, oh, this is a real bond. When this is a floppy bond, when you have large motion like this one here, this is a broken bond. So it is not counting as a number of degrees of a number of constraints. The same for the angle. Okay, so you just analyze the molecular dynamic trajectories and try to find out this number of constraints per atoms. And here is the result. So they have the C over S value here, and this is the number of constraints per atom. Remember that for atom, the number of degrees of freedom is 3, right? The good news is, yes, at 1.5, we should be able to have isostatic cement. Below is flexible, above is stressed rigid, and this is the contribution, this is the angle thing, more than the other things. And the thing is, not so much that the slope, is that in the region here, we should be able to have an isostatic cement. Which means, by the way, not yet there, that this should have some impact into aging, because this rigidity theory is applied for glasses and to predict the aging process of glasses. And isostatic glasses are known to be non-aging glasses. Nice, because now we may have found a composition around 1.5 C over S where we have non-aging cement. One way to prove this is to do a loading, unloading of the structure. Push on it and remove the load, right? So you have the volume variation here. This is for a typical CRS 1.7 that corresponds to a number of constraints of 2.7. And you see that when you unload the system, you have an unrecovered volume by 5%. So you do this for all of them, and you have this curve here. And you see that the isostatic cement, that's a composition of 1.5 here, is a guy that almost recovers all its volume when you unload the system. And that is a really good idea towards a non-aging CSH that we call gorilla CSH, to echo the work of John Morrow. John Morrow is a glass scientist at Corning. He's the one who designed the glass of your iPhone, you know? A super strong glass, right? And actually that thing was designed according to the rigidity theory, you see? So maybe there is a way to have a gorilla CSH, a non-aging CSH. Okay, from the small K. And then we can have this phase diagram with the composition, SiO2 pole here, SiO here, and water content. For this domain here, this is, well, CSH doesn't exist, basically. And then we can go from flexible to rigid, and you have a whole bunch of possible isostatic CSH. Okay? With that might be non-aging CSH. Right, now I'm going to move upscale. So this is the mesoscale CSH model. So we start from atoms. Remember the work of Jennings here. We have an idea that might be around 5 nanometers. So what we did, we designed a way, imagine that we have 2 clinker grains in water, and we see popping up the CSH grain in between them. This is what is shown here for same size particle. But what we embed that, obviously, same size particle, you end up with a packing fraction of 64. That is a porosity of 36%. But if we want to move, one way to move to higher packing fraction or less porosity, with ignoring this idea of order of cubic lattice business, is actually to manage to have a large polydispersity, so that actually you can pack small grains in between big grains. With this, obviously, you shoot up to larger values of packing fraction. And now now my next slide is to tell you about the interaction at some stage, but basically Enrico Mazzarero, what he did actually is to design a grand canonical model for the creation of the CSH gel, knowing the chemical potential, remember grand canonical chemical potential for all species, and this is what you shoot up with the chemical potential. You start by populating with a very loose structure, and then you reach a plateau here when you start having big guys, and then as you move towards the plateau, you start populating smaller guys in between the big guys. And the potential behind this is very simple, this kind of Lennard-Jones curve with a special thing in it, is that actually the strength of interaction depends on the size of the particles. Okay? So 2 big particles will have much more energy than 2 small particles, obviously. And then you can run at the mesoscale, because the size of the box is maybe 100 nano. You can do the same modeling, the same as you will do for atoms, except that now each grain may be 2,000 atoms. And now you can actually calculate the stiffness of those mesoscale models. And that's what we did here for different packing fractions, for different realization of packing fractions. And it's what we get here. You don't see very well, but behind in gray, what you have, these are the nano-experimental values of Franzum. So we do refine the behavior of the elastic modulus or the non-indentation modulus as a function of the packing fraction with that kind of approach. Okay, what can we do next? We can actually calculate hardness and compare to the experiment. This is what is done here, because this is a straight illustration of a non-indentation measurement where you have the M value as a function of H, and here are our simulation values from those models with different packing fractions. Okay, what else we can do? We can calculate small angle scattering functions. And then you see the agreement with the experiment. There is no adjustable parameters. What we say here is that a cement paste, as measured for non-indentation at 30 degrees, is maybe 53% of the low density and 47% of the high density. And we just do a weight function of this, plus some pores that are bigger pores, so to reduce scattering, and the fact that the spheres are touching each other, so we are not counting in the interface, we have to remove by the area of contact if we want to have a quantitative intensity. But you see, we do refine quite well the experiment. What else we can do? And that's the work with Martin Bajant and Elena Sokolova and Matthew Pinson, is to calculate water or nitrogen adsorption on those things. So what we do again, with the adsorption for me means ground canonical. So I do a ground canonical Monte Carlo simulation. Except that in this case, what we have here is only DFT, so it's on the lattice. Okay, fine. So it's just a simplified version of it, no problem. And then we can calculate this, fine. You see that we are missing larger point systems, so the story is not yet complete. Okay, so we have the beginning, there is not just about parameters. Everything comes from interaction, from atomistic simulation. These are prediction. Obviously, we are missing larger pore in the system. Okay, the same for water. Okay, with this lattice grand canonical Monte Carlo, fine, compared to experiment. And now what next is that actually, by using a Kelvin equation, Matthew Pinson and Martin Bajant were able to say what is missing actually. We are not having in a model all those big pores. Right now we are stuck here. So this will tell you that the story, the mesoscale story, is not yet finished. Okay? Right, now 2 words about creep and I'll be done. Creep has been for a long time a kind of interesting thing because it's not just because of cement, because this strain, irreversible strain as a function of log of time being kind of linear, at least in part. It's been seen for different, very different compounds like polystyrene, copper, CSH, concrete bridges, deflects over time, soil, and so on. So you have this what we call residual strain that is proportional to log of time, which means that the strain rate could be 1 over time, and you have a constant here, which is the load, applied load, and C is called the creep modulus, and for CSH is ranges in value between 100 and 500. Okay, what can we do with this? We can do a shear simulation of the mesoscale thing. So this is for the same size particle thing. So we have an applied strain, okay, and we can measure the stress in the box, okay? But what we can do also, we can also measure, the irreversible strain for any applied external strain. So that is a way to quantify the amount of displacement that are not reversible in the system. Okay, and then we want to link this to some energy. For this, we use the transition state theory. So now the idea is to compute activation energies for mechanical activation when I do the shear business, and and try to relate energy to the creep. So then we have a link between the irreversible strain with time. Okay? And this is what we do is that just before going down here, so just before we can calculate the energy here and take it down to 0 stress by doing and then PT simulation with pressure 0, and we calculate the difference of energy. So that will be the energy of mechanical activation just before the event here. But then we need to have 2 more corrections. I'm almost done. First, that is done without actually applying load. So if we were to apply an external load, we need to correct for it. So we assume an elastic formulation for it, so that the energy now becomes this. And you see this factor here, is that the number of particles that is involved in the shear business, because you're not shearing the whole box, actually. Only a few particles are moving. By doing so, you have now a relation between the energy and the irreversible strain, and in a very kind of physics way. We can choose an external load, say 20 MPAs, for instance, and then we can move to the creep. We have now a link between U and the strain, the irreversible strain, and time. We just inverse the relation, so we have gamma res as a function of time, and you can see that for low density CSH, we have this kind of curve with a very long portion that are linear in time. So we do find linear logarithmic behavior in time. And the reason for this is because the activation energy increases with strain. Now, finally, we need to validate this. And one way to do it is actually to try to see what is the value we have in the simulation for this creep modulus, C, and then we can compare with the measurement of Mathieu Van Dam and Franz Ulm in this PNAS paper a couple of years ago, and we have those stars that are our simulation that really are in agreement with the measurement when you plot the creep modulus as a function of the packing fraction. I think I'm done, and this is my conclusion, basically. So CSH is really a multi-scale material, and I hope I've given you a recipe how to go from atoms to mesoscale. And we spend a lot of time trying to compare our old stage, different piece of experiment we have, could be mechanical experiment, could be adsorption, could be scattering functions. But the story is not yet finished, because as I told you, in this mesoscale, we are in the small mesoscale. We still need to include the larger mesoscale. But still, we have the hope that we can upscale the same ideas. So that could be now a blob in interaction with another blob. So if you can provide some interaction rule between them, then you can upscale again the thing, okay? So, and then not only this, that I told you about the chemistry could have some impact in terms of aging. So that could be a way to engineer CSH toward a less aging CSH, for instance, or a less creeping CSH, for instance, okay? And with this, thank you for your attention. Thank you.
Thank you. Thank you very much for this excellent presentation. The paper now is open for discussion, and I invite you here the two panelists, Professor Ski from Vanderbilt University and Professor Q from Northwest University, and they will be the first ones asking questions.
Regarding the multi-scale issue, it seems like most of the things you talk about, for example, this mesoscale simulation, are the things that scale up spatially.
Yes.
What about time scale? How would it be the general recipe to scale up in time?
Okay.
And I think the second part of the question relates specifically to the nano indentation simulation that you use, mesoscopic way of doing it. Is that real-time simulation with some kind of scale at the time?
So is what?
Is that the real-time simulation? In other words, in your mesoscale simulation, is the strain rate the same as the actual experimental rate? So
let me answer the first part of it. For the creep business, it's clearly a time process, right? And I tell you that the way to go to a much longer time is to use the TST, the transition state theory, which is nowadays is called metadynamics. Basically, you explore the landscape of energy, you measure energy barriers, this is what we do, and you have a link between the height of the barrier and the rate going from one side to the other side, and the rate is just 1/time. So that's a way to actually bridge up toward very long time scales, because if I go back to the creep thing, you see this curve here, right here, this one here. This is in log of seconds, but I tell you 65, if you take exponential of 65 seconds, it starts to be a long time. So you see, so we run kind of short simulation, but you plug onto this the TST, providing that you have a good description, you hope to have a good description of the energy barriers. So that would be a way, this is the way today actually, to bridge towards very long time scales from short simulation, if you like. Second part of the question is about the nano indentation, the way we calculate it. We calculate the elastic property of the box, just like we will do with atoms, at equilibrium. So there's no rate in my simulation. Why is this? Because the rate they do experiment, well, this is very known, the experiments are slow guys. Sorry. So the way by the tip goes into the system is very slow compared to any atomic process or any mesoscale process anyway. So for us, if we want to compare to experiment, we do not want to have a rate. We want to be at equilibrium, at least at the scale of our simulations. Okay?
Thank you.
First of all, Roland, thank you very much for this wonderful plenary lecture, and it kind of opens up our minds and eyes about what is possible down the scales. But one question that I would like to ask you is, how do you upscale, or I mean, I'm trying to ask you to predict the future here, but how do you upscale from CSH to a paste to a concrete, in which now we can take these models and apply our mechanics principles for prediction? Do you have a roadmap in that regard? And the second question is, say you start to include nanoparticles.
Like silica things?
Say, even, you know, either inorganic nanoparticles or carbon,
Okay.
or possibly even slightly larger, you know, fly ash and all those new type of concretes.
Yep.
Now, what would it take for us to get there from where we have? Do we need a human, you know, genome project-like of effort, or can we do this in a more realistic manner?
Well, thank you for two interesting questions, because actually the first one, you know, how to upscale things. Actually, our idea is actually to provide the VCCTL guys, you know, the NIST guys, or whoever does those finite element type of simulation, to provide the voxel, the micron site thing with the right properties. So this is our goal is to connect with these guys, and they should be able to take on then to concrete, I mean, you know, VCCTL, the software from NIST and Hydratica and things. They do have all those concrete type of things and so on. What may be missing still is the interaction, for instance, between CSH and aggregate. Right now, Mathieu Bauchy is right here, is doing atomistic simulation of how sticky is the interface between CSH and silica, for instance. Because that obviously will be in the project. Do we always have an ITZ, interfacial whatever, transition zone? Depending on the state of the silica, for instance, the chemistry of the silica surface, for instance. So this, yes, we need to clarify those points, but clearly our next stage is to go on to provide to VCCTL the voxel, if you like. The second part of the question, can we include nanotubes, for instance, or carbon, whatever things in it? Yeah, the answer is yes, providing that we know the interactions. Okay? So in a very separate project, but in the end very related, we're doing shale gas business. Shale gas, we have kerogen phase, or carbon phase, in interaction with clays or silicate or carbonates. And yes, the interaction is the key thing for the mechanical properties. So if you can derive the interaction, yes, you can do it.
Just to follow up, so you need ReaxFF kind of models for different molecules and different atoms?
Yeah, that's for sure that we need to include chemistry. For instance, in shale gas, not cement, but you will see, for instance, the addition, the chemistry, chemical bonding between the basal surface of a clay and some kerogen phases. So real Si or carbon bonds. Mm-hmm. They are very stiff. And in the case of clay, then the mechanics will go through the clay, not at the interface, because it's a very cohesive interface, for instance. So there is no restriction. If we have ReaxFF will do the job here for carbon, because ReaxFF is very good for light elements. It's not so good for the rest. So you really the top part of the classification. Mm-hmm. But yes, for carbon is okay, I guess, for nitrogen or those sulfur and those light elements.
Thank you.
We have time for one more question from the audience. Professor Bajan.
Very inspiring and
Kidak.
interesting lecture. It invites a number of questions. One, for example, you relate the short-term creep, which was shown to be in seconds, logarithmic, to long time, and you attributed CST and TST, transition state theory.
Yeah.
Now, of course, there is also a sort of microprestress, we call it, stresses in the structure on the nanoscale, and they relax. And this has been used to show that the long time is actually logarithmic, because as they relax, the rate slows down. So are you dismissing the mechanism, or is it on top of what you argue? Is it both?
So between the nanoscale
and of course, the creep, we know in cement must be due to shear slip, affected by transverse stresses.
Yeah.
Otherwise, we would see change of stiffness. We don't.
Of course. Okay. So, well, I have a microphone, so. My answer for this is yes. I mean, so right now this is all mesoscale, so we are looking at grains in interactions here, right? Remember, the CSH could be seen as a collection of grain of different sizes, wide distribution of grain sizes. So in many ways, you can see this as a continuous phase with lots of density defects, if you like, where density fluctuates. And actually, the creep actually happens at those interfaces where the density is the lowest one. So it happens where you have lots of defects. And defects meaning, remember, in the CSH, that's where you have the largest amount of water, because you have room to accommodate water. So to answer your question, maybe at the nanoscale, what is the view at the nanoscale is the regions where you have the largest amount of water that are creeping more than the rest.
Thank you very much. It was a great way to have the end of this 2013 EMI conference. Let's thank again Roland Pellenq.
Thank you.